So this week is really about combinations and permutations using the pigeonhole principle, and then how to solve recurrence relations. So that's the topics we'll hit. In this first example, I have a bank with a password that consists of 2 letters of the English alphabet followed by 2 digits. So how many different passwords are there? So I like to think of this as the kind of the slot method. It's also using the multiplication principle. So I can think of it as 4 different positions. So there's 4 slots. So these 2 would represent the 2 letters, and these 2 would be the 2 numbers, or 2 digits, I should say. So there are 26 letters in the alphabet, so there are 26 possibilities for both of these positions. So it's 26 for both because it doesn't say that you cannot have repeats. So you could have AA or BB. So there's 26 choices for both of those, and there's 10 choices for each of these. And then using the multiplication principle, you get whatever this is. I'm going to write it as 26 squared times 100, whatever that is. Is that okay? Okay. So again, that first one was kind of multiplication principle. This second one is a permutation. So given a group of 10 people, how many ways can you select these 4 different positions? So I'm going to think about it in 2 different ways. One is kind of this slot position again. So because each of these slots have a meaning, like president, vice president, secretary, and treasurer, I can use the slot method again. If they do not have meaning, then it's harder to do it this way. So if I have 10 people, any of those 10 people could be president, but one of them will be. So I only have 9 left over to be vice president, and then only 8 left over for secretary, and then 7 left over to be treasurer. And then you can multiply out whatever that is using the multiplication principle. The other way is when the order matters, so in other words the positions have meaning, it's called a permutation. And the formula, so we have 10 people and we want permutations of 4 of them. And the formula for this is 10 factorial divided by 10 minus 4 factorial. So factorial means 10 factorial would be 10 times 9 times 6. Whoops, I forgot 8 and 7. 8 times 7 times 6, all the way down to 1. And on the bottom, I have 10 minus 4 is 6, so I have 6 factorial. So I have 6 times 5, all the way down to 1. So notice that the 6 down to 1 cancel, and I'm left with 10 times 9 times 8 times 7, which is the same as what I have right there. So again, I would go ahead and multiply that out. I did not, but that would be a permutation. So please let me know at any point if you have questions. Otherwise, I'll just keep going. Alright, so the next is, given a group of 10 people, how many ways can you select a 4-person subcommittee? So notice here, the 4 people do not have specific duties. So just to give you an example, in the last one, I could have had person A as president, person B as vice, so this was president, vice president, secretary, and treasurer. So if I just have person A, B, and C, that is different than if person B was president and A was vice president. So those are the same 4 people, but the order matters. So here, the order does not matter those two groups would be the same. And this is called a combination. So it's of 10 people, I want to choose 4 of them. And because the order doesn't matter, I need less of them. So instead of 10 factorial divided by 10 minus 4 factorial, I'm going to add in a divided by 4 factorial. So this was 10 times 9 times 8 times 7, and then, well, I'll write 6 factorial, and then 6 factorial, 4 factorial on the bottom. So 6 factorials cancel. On the bottom I have, let me change color, I have 4 times 3 times 2 times 1. So my 2 and my 4 will cancel with 8. 3 goes into 9 3 times. 3 times 7 is 21. 21 times 10 would be 210. So there are 210 ways you can make a 4-person subcommittee if you have 10 people. This next one is very similar to one of your homework questions. If we have 3 fair 6-sided dice and they're tossed, the numbers showing on top are recorded, how many different record sequences are possible? So if we have, think about each roll is different, so the order kind of matters, first, second, third. So if I have, how many possibilities for the first? I have 6 outcomes for the first, 6 outcomes for the second, and 6 outcomes for the third. So this would be 6 to the third, different sequences possible. And then how many of those, this is 216, how many of the 216 contain exactly 2 4s? So I'm going to try to explain it 2 different ways. The first way, I'm going to just think about how many ways can you place the 4s. So I could have a 4, 4, and then a non-4. I could have a 4, then a non-4, and a 4. Or I could have a start with a non-4, and then a 4, 4. So those are only 3 ways to have exactly 2 4s. But this one is actually, well, all of them really, there's 5 ways to do this. Because you could have 4, 4, 1. So I could have 4, 4, 1. I could have 4, 4, 2, 4, 4, 3. I can't have 4, 4, 4 because I need exactly 2 4s. I could have 4, 4, 5 and 4, 4, 6. So there are 5 different ways to have this kind of ordering. So all of them have those 5 ways. So you have a total of 15 ways to contain exactly 2 4s. So that's one way to think about it. Another way to think about it is there are, of the 3 positions, you want to choose 2 of those positions to be 4s. And then think about the kind of the slots. In one of the slots you need a 4, so there's only one way to get a 4. In the other slot you need a 4, only one way to get that, and the other one is a 5. So 3 choose 2 is actually 3, and then 1 times 1 times 5 is 5, and we get 15. So either way, I don't know why the first way just seems, it makes more sense to me, but that doesn't mean it makes more sense to everyone. Alright, any questions on that one? That's often harder. Alright. So if we have 13 people in a room, show that at least 2 of them must have the same, have their birthday in the same month. So this is just an application of the pigeonhole principle, and I always feel like the pigeonhole principle just seems so logical. It just tells you that if you have n pigeonholes and n plus 1 pigeons, so you have 1 more pigeons than pigeonholes, that means that there must be at least two pigeons in one of the holes, which just kind of makes common sense. So really when you have problems like this, it's a matter of associating what is the pigeons and what are the pigeon holes. So we have people, so 13 people, and then the same month. So the people are the pigeons, and the months are the pigeonholes. So there are 13 people and there are 12 months. So by the pigeonhole principle, there must be two people that have a birthday in the same month. Alright, the next one is an extended pigeonhole principle, and I keep forgetting to fix this slide. This number is supposed to be 10, not 15. So show that there must be at least 9 ways to choose 4 integers from 1 to 10 so that all the choices have the same sum. So to start with, we're going to find the minimum sum of 4 integers and the maximum sum of the 4 integers. So if we have the numbers 1 through 10, the smallest sum you could have would be summing up the 4 smallest numbers. So I'm going to call this the minimum sum, and then we're also going to do the max sum. So here we get 10, and then the maximum sum would be 10 plus 9 plus 8 plus 7. And let's see, what is that? 9 and 8 is 17, 17 and 7 is 24, 24 plus 10 is 34. So I could have a sum of 10, I could have a sum of 11, all the way up to 34. So the total number of sums if you count starting at 10 and ending at 34, you'll end up with 25. So you're really doing a kind of 34 minus 10 and plus 1, because when you subtract you don't count one of the endpoints, so we need to count both those endpoints, so we're adding 1 to it, and that gives us 25. And then we're going to look at all the different ways. So of the 10 integers, we want to choose 4 of them. So just using our formula for 10 choose 4, we get 210 that we saw earlier. And then now we're going to apply the extended pigeonhole principle, which is the floor function of the 210 minus 1, that minus 1 is just part of the formula, divided by the 25, end of the floor function, plus 1. So I just want to highlight where these numbers come from. So this 210 is that 210, and the 25 is that 25. Oh, and I don't know why I put plus 9. Plus 1, no, is equal to 9. So the floor function means if you get like 5.5, it would be 5. So when you do 210 minus 1 divided by 25, you don't get a whole number, so you just kind of round down to get an integer. And then we're going to add 1, and you get 9, and that's what we were trying to show. So we got it, check. Alright, so this one is also very similar to a homework question. Alright, the last topic is recurrence relations, and we've seen recurrence relations before. We just had to identify whether it was a recursive or explicit relation, and then find terms in that. So here we're just going to find the 5 terms again, refresh your memory on that. In this first one, these are both recursive because they give you a starting point. So here we have a1 equals 1, and then an So I'm going to say A2, so n is 2 here. A2 is A sub 2 minus 1 plus 3. Well, that's A sub 2 minus 1 is 1 plus 1. So another way to think about this is it's the previous term plus 3. So the previous term was 1, add 3, you get 4. So A3 would be your previous term, add 3, you get 7. And then A4 would be the previous term, add 3, and so on. The next one is a little bit different because it has an n minus 2 term. So this means the previous term, and the a sub n minus 2 is like the previous term, the time before the time before. So that's why we have 2 starting values, because it depends on the last 2 terms. So a sub 1 is given, a sub 2 is given, so a sub 3, now using our formula, a sub 3 is 4 times the previous term, which is a2, which is 6, plus 5 times the previous term, which is a1, which is 2. So 4 times 6 is 24, 24 plus 10 is 34. And then doing that again, I have a4 would be 4 times the previous term, which is 34, plus 5 times the previous term. So the time before was 6. And I don't know what that is off the top of my head, but that's some number. And then for a5, you'd repeat that again. So really the question that they're trying to get into in this section is, how do you solve a recurrence relation? So one of the disadvantages of recurrence relations is that if I wanted to know like a sub 100, the only way to do it right now is to find a1, a2, a3, a4, all the way up to 100. It's kind of a pain. I mean, technology can do that quickly, but by hand that's a pain. To solve it means find the explicit formula for it. And not all recurrence relations have it, but typically if you just don't have a constant term, so I have 4 times the previous term plus 5 times the previous, if I had like a plus 3 on the end or something like that, I can't solve it. So it has to not have that constant term. Alright, so here's the process. First thing we want to do is solve a quadratic, and that quadratic that corresponds to this is the a sub n is the x squared term, the a sub n minus 1 is the x term, and then the 5a, this is really x to the 0, but x to the 0 is 1, so we tend to just not write it. So we want to solve this quadratic, and by doing that I'm going to subtract the 4x and the 5 over. Then I'm going to factor. So I want two numbers that multiply to -5 and add to -4. So that means a -5 and a +1. So I get that x is 5, that x is -1. So those are the roots to my equation. And those are what tell me my general form. So in general, if I'm trying to solve this, I should put the general form somewhere else. Let me put it up top. So I'm going to call it c sub n equals u times 5 to the n plus v times -1 to the n. And the order in which you put the 5 and the -1 don't matter. So that's the general, once you find the roots, that is your general form. And our goal from here is to find the value for u and v. So what we're going to do is plug in the values that we do know. So I know that A1 is 2. So when I plug in, let's see, when n equals 1, I get, I called it C sub n. C sub 1 or A sub 1, either one, same thing. So I'll have 2 is equal to u times 5 to the 1 plus v times negative 1 raised to the 1. Then if I plug in n equals 2, a sub 2 is 6, and I have u times 5 to the second plus v times negative 1 to the second. So I have two equations that I'm going to simplify a little bit, and I have two unknowns, so I'm going to solve these two. So I'm just going to say 2 is equal to 5u minus v. And then 6 is equal to 5 squared is 25. I have 25u. And then negative 1 squared is 1. So I have, that's a really bad u. And then plus v. So I have two equations, two unknowns. There are multiple ways to solve this. You can use your calculator and see where they intersect. You can use substitution. You can use elimination. I tend to like elimination, but it doesn't matter. So elimination means you want to combine the equations in a way that the one variable will cancel out. So the nice thing about these two equations, if I just add these two, my v's cancel, and I'm left with 8 equals 30u. So now I know what u is. U is 8 over 30, which is 4 over 15. So let me think of it another way. Suppose I wanted to find a way to cancel out my u's. In order to do that, I'd have to first multiply my first equation by negative 5. So let me do that. So if I multiply the entire first equation by negative 5, I'd have negative 10 equals negative 25u plus 5v. And if I add that to the second equation, my u's now cancel, and I'm left with negative 4 equals 6v. And so I get v equals negative 4/6, or negative 2/3. So now that I have my u and my v, I can come back up and rewrite my explicit formula. So u is 4/15 times 5 to the n, plus my v is negative 2/3 times negative 1 raised to the n. This is the solution to solving the recurrence relation. Now if I wanted to find a or c sub 100, I can just plug in 100 to the formula. I don't have to write out every term up until then. Alright, that kind of covers the topics. Do you have questions?